Welcome to the final explainer in our complete C programming series. I'm honestly beyond excited for today's topic because we are tackling the ultimate capstone concept, the one thing that really separates the beginners from the pros. We're talking about memory management. Today, we're going to explore dynamic memory allocation and break down exactly how your programs interact with memory under the hood. But before we jump in, let's take a quick 45-second look back at how far we've actually come. We started this journey communicating with the computer using basic variables and operators. Then we navigated decision-making and loops and created functions to organize our logic. From there, we unlocked pointers to access memory addresses directly, which seamlessly led us right into arrays and strings. Finally, we grouped dissimilar data with structures and learned to talk to storage devices using file handling. It has been an absolutely incredible progression, and literally every single step has prepared us for what we're about to do today. All right, here's our agenda for today's explainer. We're going to start by looking at the fixed array problem. Then we'll define what dynamic memory allocation actually is, explore allocating with Malloc and calloc, deallocating with free, resizing with realloc, and finally wrap up chapter 11.
So, moving right into part 1, the fixed array problem.
We begin with a pretty major roadblock that we've hit in standard C programming. Up until now, we've used memory that the compiler allocated automatically. When we create an array in C, like say an integer array of size 3, the language has a rigid fixed rule. It reserves that exact amount of contiguous memory, maybe 12 bytes, and changing the size of that array later is strictly forbidden. But think about it. What if we don't know how much data our user is going to input? What if our memory needs change completely while the program is actively running? Well, under standard C rules, we're basically out of luck. That brings us to section 2. What exactly is DMA? So that fixed rule begs a really important question. What if we actually need memory while the program is already running? Well, that's exactly where Dynamic Memory Allocation, or DMA, swoops in to save the day. DMA is simply a way to allocate memory to a data structure during runtime. Until now, all our fixed variables lived in what's called stack memory. The stack is super rigid and totally managed by the compiler before the program even runs. But DMA allows us to pull memory from a massive, flexible pool called the heap. It lets us request exactly what we need exactly when we need it. To perform this runtime magic on the heap, C gives us a highly specific toolkit. We have 4 core functions: malloc, calloc, free, and realloc. You can honestly think of this as a system for renting and returning storage space in your computer's memory. We rent it when we need it, we resize it if our data grows, and most importantly, we return the keys when we're finished. Let's get into section 3 and talk about allocating that space with malloc and calloc. Let's break down the syntax for malloc, which stands for memory allocation. It takes the number of bytes you want as an input, and it returns a pointer of type void. Looking at the syntax here, notice how we cast that void pointer to an integer pointer, and we use the sizeoff operator to ensure we get exactly 30 blocks of integer-sized memory, no matter what kind of computer architecture we're on. Now here's a crucial detail. If the heap memory is totally full and space cannot be allocated, this expression returns a null pointer. Because of this, you should absolutely always check if your pointer is null before proceeding, otherwise your program will just crash. So how does that compare to calloc? Well, malloc takes the total number of bytes, grabs the space, and just leaves whatever old garbage data was already sitting in that memory. Calloc, on the other hand, goes a step further. Calloc stands for continuous allocation. Notice its syntax takes 2 arguments, the number of blocks and the size of each block. It allocates contiguous space, like 30 blocks of floats, and it automatically initializes every single one of those blocks with a default value of 0. Essentially, it sweeps the rental unit completely clean before handing you the keys. Just to make sure you're tracking with the syntax, I want you to pause and try this quick quiz straight from the handbook. Try writing a short C program to create a dynamic array of 5 floats using malloc. Remember, cast your pointer to a float pointer and use 5 times size of float in your argument. Active practice like this is really how the concepts stick. Real quick, if this series has helped you learn C programming, don't forget to like this explainer and subscribe. And if you have any questions at all about pointers, malloc, or calloc, please leave them in the comments below. We love seeing your progress.
Moving on to section 4, deallocating with the free function.
The syntax for free is beautifully simple. It's just free, and then your pointer in parentheses. And this is incredibly crucial because the heap memory you allocate using calloc or malloc is not deallocated automatically when your function finishes. You requested it manually, which means you have to release it manually. But here is a huge best practice warning. Once you free a pointer, it becomes what's known as a dangling pointer. That's a pointer that still holds a memory address, but you no longer have the right to use that address. So always set your pointers to null immediately after freeing them. Think back to our rental analogy for a second. If you don't release that pointer using free, your program is going to hoard that space forever. In programming, we call this a memory leak. The computer thinks that memory is still actively in use, even if you're totally done with it. If your program keeps doing this over and over, it will eventually run out of memory entirely. So write this golden rule down. To prevent memory leaks, return your rental. Every single time you type malloc or calloc, you should immediately be planning exactly where you're going to type free. Next up is Section 5, resizing with the realloc function. So what happens if our rental unit is suddenly too small? Or maybe even too big? Well, reallo allows us to upgrade or downgrade our memory size dynamically on the fly. To do this, reallo takes two arguments, our previous pointer and the new required size. It seamlessly takes your existing data, finds a completely new contiguous block of memory that fits your new size requirement, moves your data over, and updates the pointer. It's literally like your landlord instantly moving all your furniture into a bigger apartment for you. And finally, Section 6, our Chapter 11 wrap-up. Take a look at this Chapter 11 practice set straight from the handbook. I highly encourage you to work through these problems to truly cement your understanding of dynamic arrays. For example, Problem 4 asks you to dynamically create an array storing 5 integers, and then use realloc so it can store 10. Honestly, doing these exercises is the absolute best way to bridge the gap between just watching an explainer and actually writing functional C code. Let's do a quick recap with these 5 key takeaways. Number 1, standard arrays on the stack have fixed sizes determined by the compiler. Number 2, dynamic memory allocation lets you request heap memory at runtime. Number 3, malloc and calloc are how you rent that space, with calloc adding the bonus of resetting the values to 0. Number 4, free is absolutely essential to return the memory and prevent memory leaks. And number 5, realloc allows you to dynamically resize your arrays on the fly. Congratulations on completing the entire C programming series handbook. You have gone from writing your very first lines of code to manually managing system memory like a true systems programmer. Please remember to revisit previous chapters anytime you need a refresher, because foundations like pointers and basic variables tie directly into everything we did today. Thank you so much for joining me on this incredible journey to master C programming. Now that you have the power to control your computer's memory directly at runtime, what incredible unconstrained systems are you going to build next?